Hi, this is Purple Tiger, and today I'm going to share some of the math that was presented in Math for the Planets, but had some errors that I promised to fix. I made that video about a year ago, so this is the fix. And it was really just a discrepancy between the velocity for the planets and their periods based on this whole system that I've come up with that postulates that the Earth and Sun and Moon, as a solar system, are part of a black hole system. And that shouldn't be construed as anything negative. It's just a different way of seeing everything. So let's start with the equations. All the background is in the first video. So I'm just going to go right into the fix. What I've done is made a symbolic treatment to simplify the presentation so that this first figure, delta, corresponds to the speed of light, 186,282.3959 miles per second, over a rotational element, 2 pi squared, and they both have the same exponent. So they can be grouped as delta and then with the exponent. Then the one to the right there is the event horizon for a black hole, a distance on the top, and then on the bottom is the number of miles in 1 degree of the Earth's circumference at the equator. That is grouped under the symbol nabla. Those always have the same power no matter what, so that's called nabla. Don't really need to know the name of the symbol, just know this upside down triangle. All right, so here we have the day equation using the symbols and the distance. So I'm going to use a notation because that distance is an inverse distance. So if you take, for example, Mars, and it's like 1.5 AU. Then what you do is divide 1 AU, which is the Earth, by 1.5 AU, and that gives a ratio that's an inverse ratio, because usually it would be 1.5 over 1, and that inverse ratio is applied to the Earth to get an inverse distance. That's what that distance is. And then we have the symbols for the other two parts that correspond to what I just covered. So that's the simple day equation. Distance to day, based on Kepler's third law. Now, I had to decide whether to use a distance to day equation so that distance is the base value from which all the other equations are derived, or day to distance, in which case day value would be the base value. But it turns out that distance to day is the easier transformation. So using distance as a base value makes the most sense. There's one more thing before we get into the next equation, which is quantum values. You see here 3 quantum values, 40.5, 67.5, and then 45,562,500, which is 6750 squared. All those values are to the 1/2 power, but they're all to the same power no matter what. Those are represented by the symbol of a 3x3 grid, which is a quantum set, a quantum being just a number. So those are 3 quanta. Here we have the quantum velocity. Using the symbols here, the first 3 terms of the quantum velocity are the inverse of the day value, which is computed from the distance. So that's the first equation I showed you, but now in symbolic notation, and you see the distance is a global target, that's the GT at the bottom, and you're taking the inverse of the global target, whatever it's going to be. So the target is the planet. So if it's the Earth, then it's going to be 92 million miles. If it's Jupiter, it will be the inverse of 480 million miles. So those distances to the planets are givens, And we're working from those givens to this quantum velocity. The fourth term here is a non-quantum velocity term. You take the non-inverse distance cubed times 2 pi, which gives you a cubed circumference in miles, and then divide by seconds. So we've got the first three terms, which are the inverse day, and then the fourth term, which is inverse hours times seconds. 3600 is minutes times seconds, 23.93 is hours. And that is a cubed term. The first day term is also cubed because you can look at the day term that I gave you before and you can see that these things are cubed. So all of this is cubed except for the 2 pi to give a velocity. And that's mainly all there is to the quantum velocity, is that everything is cubed. The quantum values at the very end, represented by the grid symbol, are inverted. And that's it. So those values look like this. This is the third column here, quantum velocity. And you can see it goes from the moon's value of 0.64 miles per second to 1.12 times 10 to the minus 2 miles per second for Pluto. Now, we're going to move on to the mass radius. What is a mass radius? So mass radius is simply part of the equation for angular momentum. So you call angular momentum J equals mRV. mR is mass radius, V is your quantum velocity. And we won't get too much into angular momentum, but as background, it was useful to figure out if I was doing the right thing here. Here we see that everything is flipped. Everything is inverted. So if you look at what's in the square bracket here for the mass radius on the right, we have the inverse of the velocity, basically. We have delta to the 3/2, nabla to the 9th, but not 1 over. These are just non-inverse values. That's because the first three terms in the square bracket are the day value for, again, a cubed seconds and hours. 3600 seconds times minutes, hours, 23.93. The whole thing is seconds, but it's now on top. And on the bottom, they have the same thing, but now it's on the bottom. So it's completely flipped. And then what you do is take that to the 3/2 power and multiply by this left-hand term here. And so you can see everything on the right in the bracket in the second equation has been reduced or simplified just to be shown as the inverse of the quantum velocity squared. And then we have this term on the left. The quantum velocity is always less than 1, which means that as you get farther out, the mass radius gets larger. And the mass radius looks like the first column in this table. It starts out as the radius of the Earth. For Pluto, it is less than the radius that we observe for the moon. Let me point out here that all these columns of numbers are contiguous in a way because mass radius extends from the Earth's surface to a distance of 198,000 miles. Marker distance goes from the moon distance, 239, out to 13.7 million miles. And then actual distance goes from 16 million for the moon, and we'll talk about that, to 3 billion miles for Pluto. What is this 16 million? So all that is a transformation of the moon's orbital period by the Earth's orbital period, given that the Earth has a distance of 92,634 or 370 miles. That gives you a implied distance of 16.4 million miles for the moon's orbit. Now, there's been no observation of a planet inside the orbit of Mercury. So this is purely theoretical. But on the other hand, those marker distances are distances that would apply to a black hole that has a diameter or a radius of 13.79 million miles, assuming that Pluto is the outside edge of the gigantic black hole. And that corresponds with the size of the black hole at the center of the galaxy, which has the exact same radius. And then we have the marker distance here. So the marker distance has a few little derivations here, but it's not too bad, and it's the last thing we're going to look at. So what this first one is doing, and it's equation 49, if you look at the paper that's available, which is Math for the Planets Part 2. It's on the Notion website that's linked in the description. We're taking the quantum velocity and reducing it to a radius. That's what this first thing simply is. So what would normally be miles per second, you cancel out the seconds with this first term here, day times 3600 times 23.93. That cancels out the seconds, and then you divide the circumference that's left over by 2 pi, and that gives you a radius, and that becomes the marker distance. But what does it show at the base level? Okay, so remember, we're deriving everything with base values of distance. I know I've lost about 99% of the audience at this point. Here's the first equation, just in terms of base values. We have the inverse day value to start out with. This is not cubed, and it's not velocity squared. This is just regular velocity. We have the square root of the uncubed actual day value. So it's actually the first equation I showed you, the distance to day equation, but square rooted. All right, that's all that's going on here for the day value. It's inverse day value. Then we have the non-inverse distance being used for the velocity, the regular velocity, on the right-hand side. And then we have the division by 2 pi, as shown in the first top equation for the marker distance. The original 2 pi to the 1/2, again, this is just square root. And then we have the quantum term at the far right side, square rooted. So the whole thing is square rooted. But what does it mean? We don't know. So we're going to keep going here. We're going to push this thing. We're going to push this equation. So the second derivation replaces the first 3 terms with this 1 over day to the square root, right? Just to simplify things. And then the rest of it is pretty much the same. The second derivation can be re-expressed as this third derivation, equation C1. This is the cake. This is what we're really looking for. So in the square brackets on the right-hand side, on the top we have 3 circumferences. Well, what in the heck is that? It turns out 3 circumferences describe a 3 torus, or what's called a hypertorus, which is a torus in 4 dimensions. It's represented in topological language or in group theory as S1 times S1 times S1, where S1 is the circumference of a circle. And that's exactly what we have here. We have a cube of S1, S1 times S1 times S1. That is divided by a day value and the seconds value, as we see in the second derivation above. So this is a pseudo velocity, and we're treating it actually as a volume because of that cube term. And by taking the square root of a volume, you're taking S1 times S1 times S1 and looking at S1 times S1. But before we go further with that, let's look at the left-hand side. We have the inverse of the quantum term, which we don't do anything with, we just keep that there, divided by 2 pi squared. Now 2 pi squared is equal to 4 pi squared. 2 pi in parentheses squared is equal to 4 pi squared. 4 pi squared is part of the surface area for a hypersphere, or torus, not a 3 torus, but a 2 torus. And so that's 4 pi squared, little r, small radius, minor radius, and then the big radius r, which is the outside circle of the torus. Minor radius is the perimeter of the figure, which is swept around the axis at the center of the torus circle. That's basically what that is. So what does this all mean? It means that we've got a surface area after you take the square root of the 3 torus. It's hard to imagine, but that's what's going on. Divided by the rotational element, which is 4 pi squared on the left here, leaving what we can call a line velocity that's a projection of the 4D torus, which is really cool. That is really, really cool. And that projection is the marker distance. In the marker distance, the first value of the marker distance based on distances of the planets is exactly the moon's distance from the Earth, as we can see in the second column here, 239,812 miles. That's the average value. So wow, this reconciles the moon and its position, not only with the Earth, but with the entire black hole system, making the moon the innermost horizon of this N torus, which has many leaves. So those leaves can be demarcated by what's called a Hopf fibration. And here's a picture of a Hopf fibration for a 3-sphere as opposed to a 3 torus. So a 3-sphere is just a little bit simpler than a 3 torus, but it's the same idea. And you can see these leaves of what look like toruses that are embedded in each other, extending out from a center. And that whole thing would describe the interior of a black hole. So the outermost horizon, or the outermost boundary of that black hole, would be at 13 million miles, because we're assuming that that's going to be where Pluto is going to mark that. So in this table here, the marker distance, the last one is 13,799,000 miles. And again, that corresponds to the black hole at the center of the galaxy. And then you have all these areas, embedded things inside the black hole, which act as reflecting horizons for what we see from the Earth, which is at the center of the black hole, reflections of the planets. So if you take the marker distance in whatever form, it's always going to give you the same value. These 3 derivations all give the same value. Multiply that by 2 pi to get a circumference, and then divide by the quantum velocity, which is this thing up here, you will get the day value, the orbital value for the planet that you're solving for, which is pretty damn cool. So that is it, my friends. That is it. This is the correction and the math for the planets, with the assumption that all of the things we see are within a black hole horizon and system, and the Earth is at the center, which goes completely in the face of everything that has developed since the time of Copernicus and Galileo, and strangely enough is in accord with the ancient thought of the Greeks. There are many different ways of looking at things. This is a newfangled way that is similar to an old-fangled way of looking at the solar system.